All right, good morning. Hey, everybody, this is Mr. Willis. I just wanted to let you guys know that I'm going to start putting a couple of these lessons online so you guys can get some of this information before the end of the year. I know there's a lot of uncertainty as to what kind of stuff school's going to be able to do over these next couple of weeks, but I still want to give you guys the opportunity to learn the material that we're going to go over. So, what I'm going to do is I'm going to post this material. This is a set of notes and diagrams that I have collected, put together for you guys so you can utilize this at home. And what I'll do is I'll do this and I'll create some kind of quiz for later on in the week so that you can go ahead and use the notes to try to answer those particular questions. But what I'm going to be talking about today is plate tectonics, right? So I've got a couple of sources that I'm going to use for you guys today. I'm going to try to make some marks on the screen here for you, but we're going to talk about plate tectonics. We're going to talk about plate movement and why these things are moving in these different directions here and what we think is going on. So you guys know I draw terrible, so I'm also using a mouse to draw on this, so you guys are going to have to bear with me a little bit. So I'm going to go through this. We're going to talk about these particular things here with plate tectonics. I'm going to give you guys some of these websites to take a look at. There's some really interesting videos that you can go through. I'm not going to spend the time to do that. But the whole idea here is that we're going to take a look at the underlying mechanism of plate movement, where the whole idea came from, what's the conceptual understanding that we need to know for this, and why it's important, right? So we're going to take a look at this. So I've got a couple of different things, and I've got some websites you guys are going to be able to, you can get to all of these links specifically at the bottom of the note page, which I'll share with you guys at the end of the lesson here. So everything from these seismic monitors to show where the earthquakes are going on right now, all the way back to the notes that we're taking a look at here. So again, so what is this whole concept of plate tectonics? Plate tectonics is this understanding that something is causing the Earth's surface to rearrange itself. And the history of this idea is pretty complicated, and it's really new whenever we talk about geology in general. There's a couple of guys, and we've mentioned them in class before, and I'll kind of highlight them here for you. Antonio Snyder is going to be one of the first guys that kind of comes up with this concept that the plates look like puzzle pieces, right? That was really just his introductory idea to these particular things. Alfred Wegener, who's going to be the guy that we would have been talking about had we not had to deal with the COVID issue, is a super interesting guy. He's going to be a meteorologist in Germany, and he's just going to be kind of a science junkie, right? So he's going to be, kind of flipping through some books one day, and he's going to notice that, again, that the continents jumped out to him, in particular South America and Africa kind of jumped out with the outline of those continents. I'll bring up a little map here on Google Earth if I can. So that we can take a look at this thing real quick. Let's launch this so you guys can kind of get an idea of what we're looking at in these particular cases. But he noticed that the outlines of the continents looked very similar in some locations. And he started to try to figure out why. Was it just a coincidence, right? So if we're looking at this here, no, I don't want to see the 5 things about the Earth. So let's... All right, world's mine. All right, so if we take a look here, obviously you can see, if I'm going to have to figure out how to get rid of the cloud cover. This is a little different than the version I have at school. But you can see where the sub-Saharan Africa is, where Congo is here, the Congo River Valley, the Amazonian River Valley here. These two areas look a lot like they could connect. So Wegener is going to come up with this idea of what's going to be, what happened. So he kind of coined this term Continental Drift. So he's going to notice that not only do the shapes line up, which is what I have for you guys right here, the shapes of these continents are going to line up. He's going to have fossils of land animals that are going to be connected. While these arrows are really big, I apologize. And he's going to notice that there's some areas in particular around Africa that are going to have glacial scars. Now, the issue with glacial scars being in Africa is that obviously that is a very, very hot part of our planet. So he asked a couple of questions here, and those questions, let me see if I can figure out how to make the pen smaller. All right, and some of those questions related to how in the world did those things get there? And one of his ideas that he threw out was that maybe these places weren't in the same locations that they had been previously. So he went and he looked for some evidence. So some fossils that he's going to find. He's going to find a number of different animals. Mesosaurs, he's going to find some, and they're going to be located in some areas. One of the more interesting one is about a 4-foot, 5-foot crocodilian animal. It's called a Mesosaurus. And he's going to notice that there were fossils for this guy in South America, and there's fossils for this guy in Africa, and there's fossils for this guy in Madagascar, and there's fossils for this guy over here in India. So his idea was, okay, how can a 5-foot crocodile cross some oceans to get to these areas? And this is when he's going to come and he's going to kind of get to that specific understanding that maybe these continents were connected, right? So that idea of Pangaea is going to be the one that he has. Now, Wegener's idea had an issue, right? And the big issue was that he really didn't have a good thing that could cause this mechanism. So whenever he's going to share this idea with his fellow geologists in the early 1900s, he's going to be ridiculed. They're going to make fun of the guy. They're going to be like, yeah, let's go outside and watch the Earth move. And he's never really going to get the credit that he really deserved, because this is going to be one of these cases in science where he almost got it perfect. He just, again, without the evidence, that's not something that scientists can utilize to work with. So he's certainly going to have some trying times with that. And what I'll do is I might edit this here, and I'll put you guys a little link to Alfred Wegener's life. He's not going to let this stop him. He's going to continue doing research, and in particular, he's going to find some really, really interesting fossils in Antarctica that are going to be integral to our understanding of these ideas. All right, so fast forward another 30 years down the road, 1941 to 1945, a really, really important event occurs on Earth. Hopefully you guys are familiar with World War II. And what's going to happen here, you can see where I'm highlighting this, is that we're going to get a lot more understanding of what's going on under the ocean. So Wegener was looking on land for the evidence to support his theory. And frankly, there isn't a tremendous amount of evidence to support that movement there, because we don't think the cause is there. We think it's underneath the oceans now. Now, back in 1915, 1916, when Wegener is doing his research, obviously getting down to the bottom of the oceans is going to be problematic. Not only that, but it's going to be very difficult to get accurate maps of the bottom of those oceans. So Wegener never really gets the evidence. Now, fast forward to 1941 to 45, the German U-boat fleets are out, the Americans, the Japanese, they all have submarine fleets that are all over the oceans. They are crisscrossing the Atlantic, they are crisscrossing the Pacific Ocean here, and when they're doing that, they're trying to find each other. So they're going to use a piece of equipment called sonar, which is a lot like radar underwater. They're going to be bouncing sound waves off of things trying to locate objects in the water. So what the side product or the byproduct that they're going to get from this is an understanding of the bottom of the ocean, because when you're not hitting another submarine, these sound waves just go all the way down to the bottom of the ocean and they bounce back. So it allowed us to generate some pretty accurate maps of these particular areas here. So in version 2 of this video, as I mess around with this a little bit, I'm going to get rid of the cloud cover. I'm going to load the plate boundaries here, and you're going to notice that, and if you guys can remember back to the classroom version where I show you this, there are ridges that appear in the middle, and you can zoom in here. Oh, look, my mouse wheel works here. Perfect. So we can see these scarrings here, and this is an area where we are seeing movement, right? So this is something that is popping up in these particular areas here. So we've got movement of this plate going this way and this plate going this way, which is causing this ridge here, this mid-ocean ridge, the mid-Atlantic ridge, which is the longest mountain range on Earth. There are a number of underwater volcanoes. So this is the thing that we found while looking for submarines all around these particular areas. So let me clear this off here. And as we get back over into the Pacific Ocean, same thing, right? We're going to see Hawaii. We're going to see all these striations and scars here. We've talked about the Marianas Trench, the Northern Marianas Islands. We've talked about Challenger Deep. And this is going to be an area that we're crisscrossing with submarines in a quest to sink Japanese vessels during World War II. And it's going to allow us to get these really accurate maps of the underwater of the ocean. So scientists are going to get this, and they're going to notice that there's these huge ridges and things that are popping up. And as we learn more, we're going to notice, and we're going to find more evidence along these things, and I'll show you guys this on the chart in a moment, that there's movement here. The Pacific Ocean is getting squished in a variety of locations here, and we're getting these ridges that form along these areas here. This is an entirely different plate, and it's getting run over. And whenever you do that, you have lots of friction, you have lots of rock melting, so you're going to get lots of volcanic activity, and you're going to get lots of earthquake, seismic activity. So let me zoom out here, get rid of my drawing here on the screen. And again, the Ring of Fire is something that we're going to see here. So this again gives us a really good view of just how big the Pacific Ocean is, right? So it's almost half the planet. But the entire Pacific Basin on the outer rim here is, wow, that's a really big line, is being squished, right? So the continents, we've got Asia moving in this direction, we've got North America moving here, we've got South America moving here, we've got Antarctica, which is trying to move north, and we've got Australia, which is moving here, which is causing this to get squished up. So all of these are going to be things that we find as a result of Wegener's idea, right? So let's go back to the notes here. That didn't work. Clear the screen again, switch to my cursor again. All right, so we're going to have this. So some interesting information that we have about this, and one of the things that I have for you here, this link right here is going to lead you to the NOAA organization, the Atmospheric Institute, and the Ocean and Atmospheric Institute of the United States. They have a link for how old the crust here is on the Earth. And one of the things that we see here, the area in red you can see is really young, less than 20 million years old. So hopefully you can see these lines, these ridges that pop up in these particular areas, and these ridges are going to be surrounded by brand new crust. So what's the takeaway from this? The takeaway is this is areas where new crust is getting created. So new crust forms at these ridge lines that we see here. Old crust, and that older crust that we had just looked at on the Google Earth video right here, is getting overrun and getting squished. So this is a way that we can recycle crust back into the Earth. So new land gets created, and the byproduct here, the byproduct of these particular events is going to be that the continents are moving, right? And as they move away from each other, we've got Africa moving in this particular direction. All of these continents, they're moving away from these particular locations, and they're going to cause a large variety of geologic processes that we're seeing in these particular things here. All right, so back to the notes. What I listed for you here were the 3 big pieces of evidence, or 4 big pieces of evidence that we use today to kind of support Wegener's particular theory on these particular ideas. First off, the ocean floor is basalt. And you guys know from the big chunk of basalt that I have in my classroom that extraordinarily hard rock, it forms when volcanic processes occur in cold water, and the ocean floor is 99% of it. So what does this tell us? That a huge amount of the ocean floor is igneous rock that was created in these volcanic events. Where were these volcanic events taking place? Right here on these mid-ocean ridges that we see surrounding the planet. So these are the areas that are creating the crust underneath the ocean floor itself. Obviously, magnetic striping of the seafloor, this is something I'll try to get into a little bit more, but the magnetic poles of the Earth, they flip occasionally. And when they do that, the iron particles, you guys know that basalt has iron, we've stuck some magnets to it in class, that whenever those magnetic particles, when the iron is in the lava, the particles can move. So whenever the lava solidifies into a rock, those iron particles have lined up with the Earth's magnetic field. So we can see that in certain rocks, these fields of iron, the iron that is in the rock itself, is going to be flipped in different directions, which tells us that these layers of rock were created at different time. This is the evidence is suggesting that these particular things are taking place. So this is going to be a really, really important piece of evidence. Earthquakes and volcanoes. Again, I'm not going to insult you guys. MOR, if you see it in my notes here, stands for mid-ocean ridge. But there's going to be a variety of places around the Earth. Volcanic activity, seismic activity, earthquakes, all those forms of activity tend to be in large concentrations along plates, right? So let me see if I can make this. Oh, yeah, here we go. We'll go to the large version here. So you can see those plate boundaries. These are areas that are getting overrun and squished here. We can see the Pacific Northwest, where the San Andreas Fault here is. We've got the Nazca, the Juan de Fuca plates. We've got the Atlantic plate over here. We've got the Australia. We've got Micronesia, these particular areas here. So all of these areas, these plate boundaries, are filled with seismic and geologic activity. This is just another piece of evidence that we use to support the idea that our planet is still moving around, that we still have these things taking place. All right, so seafloor created at the mid-ocean ridge. Let me go ahead and fix that. By the melting of the underlying mantle. And I left some ideas and some terms here that you guys can add into your notebook, and you can use Google to review those particular things. All right, so the oceanic crust moves away from the mid-ocean ridge. Think of it kind of like a conveyor belt. Think of it like the little trolley that moves things at Walmart. You put things at the end of the belt near the end of the aisle, and it moves them towards the front. So they're going to be carried along with this. Now, the additional benefit that we're going to see this, or not really benefit, or just a result of this, is that when these things collide and get pushed underneath the continental crust, they're going to exert a force. And that force is going to be what we think is the driving, it's what's driving the continents around. It's pushing them around on the Earth itself. So continents move with oceanic crust, not through it. So they don't collide and cut through each other, but they bump into each other. Think of it as a really, really slow version of bumper cars. And then the oceanic crust gets consumed at subduction zones, right? So going back to our chart, our map here, the Marianas Trench and the Marianas Islands, which have a really interesting historical context here. We talk about the nuclear testing and things that were done here. But these islands, while not only being beautiful, are located in one of the deepest trenches on the planet. Challenger's Deep, if memory serves, is somewhere around 36,000 feet deep. Again, you could dump Mount Everest in there and still have 6,000 feet of water. So what's happening is the crust is getting pushed underneath the Marianas Islands in those particular locations. All right, so we have that. So the whole idea here is seafloor spreading, which is the modern information that we've added to continental drift, which was Wegener's idea, gives us our modern theory, which we call plate tectonics. So the basic breakdown of plate tectonics is that we have a couple of different layers of the Earth, which I'll try to make a video for you guys next. The outer area, the rock layer of our planet, is called the lithosphere. So you guys know from Latin that litho means stone. It's formed of solid ridged plates. It forms the outer shell of the Earth, and there's two types, right? There's continental crust or continental lithosphere, and then we have oceanic lithosphere. So those two things are going to be between 100 and 150 kilometers thick, especially in mountainy regions here on the continents. And oceanic crust can be pretty thin, right? So these are kind of just some conservative estimates. There are areas of the planet where this crust is a lot thinner. The Marianas Trench is a great example of that. The Asthenosphere, which is the upper part of the mantle and the welded part of the lithosphere. So basically what I want you guys to understand is we got a lot of hot rock. And hot rock is going to get kind of gummy. Imagine you've got some Hershey's candies in your pocket and you leave them in there for an hour or two. What's going to happen is that chocolate is going to stick to the candy wrapper. The candy wrapper here is the lithosphere, and the chocolate is the asthenosphere. They're going to get stuck together. They're welded. So as the asthenosphere moves, the lithosphere is going to move along with it. So the melting is going to take place at the mid-ocean ridge by decompression melting. Whenever you deal with water, you deal with pressure, you can change the melting points of some things. Again, another highlighted word, I'd like you guys to add that into your FOSS notebooks. Or you can type it on a Google document, guys. I know we're trying to work through this here. I just want to give you guys some more science as we move through this. We've got plate boundaries, right? So, and these words are areas, obviously, where plates are going to collide. There's ocean plates, there's continental plates. Those are going to be the two flavors that we're going to be dealing with, and we're going to be dealing with what's going on at those areas. So for divergent plates, we're going to be dealing with mid-ocean ridges. Okay, they're spreading centers, and we do have a divergent boundary here on Earth itself. Let me zoom over here to it in Africa. You can see right here, this is a diverging boundary. You can see where it's starting to peel apart. Scientists hypothesize, evidence suggests that when we take a look at this here, that this particular area here is trying to peel away from Africa. This part of Africa is kind of moving in this direction. This part is moving in this particular direction. So what's going to happen here is what we think would happen with Madagascar down at the bottom. That this area of Ethiopia, Somalia, Kenya, which is, the cradle of life as far as hominids are concerned, is going to get peeled away and pulled here. It's incredibly volcanically active. It's a really, really interesting scientific area. It's also an area that's undergoing a huge amount of political strife at this particular point. But Ethiopia, Somalia, Kenya, and again, the Sudan and Uganda, this is where we're going to be taking a look at this. And you guys can see here, this is where the Nile River runs up in these particular areas. So lots of elevation loss here. So this is going to provide the mechanism for water to move in these particular areas. All right, so back to where we were looking here. Let's go back to the notes. Let me get back to my pointer here. So we've got divergent plates, which are going to be areas where they move apart. You guys can fix my grammar stuff later. Convergent boundaries are going to be where things come together. There's three types of convergent boundaries. There's ocean to continent, right? So think about the edge of North America. We've got a plate here. You can see the continental shelf right off the coast of North America. And we've got the Atlantic plate, which is moving in this way here. All right, and we've got North America, which is kind of getting pushed, but we're still going to have this area where these things collide. So we're getting kind of shoved in front. Imagine somebody's pushing a buggy behind you and hitting your buggy, right? So that's kind of what we're seeing in this particular area here. So this is going to be a continent-ocean collision. And there's going to be some other ones where there's going to be some more where both of them are going to be traveling in the same direction. This is not an example of that, but we're going to see lots of volcanic island arcs. Japan would be a great example. The Aleutian Islands, let me zip over there to it. Here is where we've got the North American plate, at least the edge of it here. We've got the edge of the North American plate. We've got the Eurasian plate that's located right here. This one's traveling in this direction here. The Pacific Ocean is getting shoved here. And what do we have here? I showed you guys this whenever we looked at the video. We've got lots of volcanoes. Let me draw a terrible volcano here. Kind of looks like a tree. All right, but that's what we're going to see here. And these volcanoes created this island chain that is located here. That drawing is terrible. You guys know how that works. So that's going to be those types of plate collisions. All right, so we're going to move on. We got ocean-ocean plate collisions. This is going to be what's happening in the middle of the Pacific Ocean, where the Marianas Islands were. We're going to get one plate's going to get shoved under the other. Now, typically that is a function of density. The denser, heavier plates, which are ocean, remember, think about that basalt rock, very heavy, very dense, is going to get pushed underneath the lighter plates. Now, when two ocean plates collide, it just really depends on the specific kinds of rock that are colliding there. One of them is going to get shoved under the other, and you're going to get a series of mountains that are created in these particular areas here. So our volcanic mountains. So you're going to get these volcanic island arcs. So we see it here in Japan, we see it in the Marianas Islands, we see it along the Philippines, Papua New Guinea. These areas here are incredibly volcanically active, and some of the most dangerous volcanoes on the planet are because of these ocean-ocean collisions and these ocean-continent collisions. And then we have two continents colliding. Now, a great example of this here is India. India used to be an island. We actually classify India as a subcontinent, and it was located way in the southern Indian Ocean. And it's traveling this way still to this day. And we've got we've got the Eurasian plate, which is moving in it's a huge plate here. And we have this collision zone right here. It's kind of a crumple zone. So India is still trying to push into this area here, and it creates this large, seismically active area. There's not a lot of volcanoes in this region, but there are going to be a huge amount of earthquakes. And not to mention, when you've got two of these things that are colliding, you're going to get a very interesting phenomena that's going to occur. Namely the Himalayan Mountains. And if you guys have paid attention to the news at all during this COVID break, global air pollution has dropped so much in northern India that from India, 100 and something miles away, they can see the tops of some of these Himalayan mountains for the first time in 30 or 40 years. So these mountains are huge, right? K2 and Mount Everest are 28,000 feet plus tall in this particular area. So, and then we've got transform boundaries. This is an area where two plates slide right by each other. So I'm going to zoom back out here. We'll flip this out back to the United States and the San Andreas, right? So for those of you who saw that awful movie, we've got North America kind of moving in this direction, and it's kind of more of a collision here, but we've got a chunk of plate here that's running. And what happens is you get lots of pressure that builds up along these crumple zones, and along those crumple zones you get stress. And as that stress builds up, you are going to get activity and volcanic activity. You're going to get volcanic activity up in these areas here. There are some volcanoes located throughout these particular areas, but you get lots of earthquakes. All right, so which is why we're always super concerned with what's going on in these particular areas over there. All right, so moving on, we've got the motion of these plates here is largely due to the convection in the mantle. Remember, convection occurs. Hot stuff tends to rise because it's less dense. Cold stuff tends to settle because it's more dense. And as it moves down in these areas, and as these huge plumes of material move through the mantle, let me see if I've got a picture of that. As this material moves through the mantle, it's going to cause this material to move along. All right, here we go. So this stuff moves up, and it causes things to move away from those mid-ocean ridges. So just like when you cook a cake too long in the oven, you get a big crack in the middle because that liquid cake batter is moving. The less dense stuff moves, the cooler stuff moves down the sides, and heat's got to get released. And if you leave it in there slightly too long, you get that crack that forms in the middle of the cake, right? And that's going to be a perfect example of what's happening on the Earth. The crack in the cake is that mid-ocean ridge that we're seeing here on the globe, right? So that's going to be really, really important for us. All right, so the kind of the key takeaway here, if we don't have plate tectonics, we don't have volcanism, we probably don't have an atmosphere that functions the way we do. We think the initial carbon dioxide that occurred on Earth occurred through this volcanic activity. We think this for a variety of reasons, but we can also look at Venus. The Venusian atmosphere is full of carbon dioxide, and there's no animals breathing that stuff out. But one of the interesting things about Venus is it's probably the most volcanically active place in our solar system. So we see huge amounts of carbon dioxide and sulfuric dioxide getting pumped out in these areas, and that material is going to get pushed into the atmosphere. And again, life evolved on Earth to take advantage of those molecules. And again, we're going to see the rise of those aerobic respirating organisms on the planet to take advantage of that carbon dioxide. And to give off the carbon dioxide and to use the oxygen. And then the final thing that we're going to see here are hotspots. Hawaii is a great example. The Yellowstone caldera is a great example. Just there's spots on Earth that are hotter than others. And they're so hot, in fact, that that lava, that magma material underneath the surface of the planet, burns its way through the crust and digs its way out and erupts, right? So we get these interesting hotspot basaltic shield volcanoes, which I'm going to make a little video about later on for you guys, that occur at these hotspots whenever they're in the ocean. Whenever they occur over continents, it causes a different issue. We'll talk about that later on. Okay, so the big takeaways here. Plate tectonics is the thing that drives the majority of the rock cycle. So remember we were talking about the rock cycle before you guys had got out. And the rock cycle is going to be the mechanism for all of these things to change from igneous rock back into sedimentary and metamorphic rock. And the input there is going to be heat, it's going to be erosion. All of those things are going to play a role depending and to create those types of rocks that we see. So this plate tectonics is a huge recycling system. So what's going to happen is that sedimentary rock, metamorphic rock that's at the edge of plate boundaries gets recycled back into the Earth's crust. It gets melted, and then again it's going to erupt somewhere else. And that material is going to create new igneous rock on the surface of the planet. So this is how we know that this rock cycle is a continuous process that's going along in these particular things here. So igneous rock forms at mid-ocean ridges. It gets subducted, and metamorphism occurs. So you're going to get lots of heat and pressure at these areas where they get pushed against each other. They're going to melt. Some of it's going to melt. It's going to create igneous rock, and that's going to form granite, igneous granitic rock. The erosion of these continental rocks provides sediment. These sediments are deposited in the ocean, which is where we get a huge amount of our sand. The sedimentary rocks form here on Earth, where we see all that limestone. We see all those different types of sedimentary rock that we saw, shale and those things. And then for us here as humans, we're really interested in these forms of rock. Why? Fossils, right? So the sedimentary rock is going to be in those particular areas here. So what I've connected to you for you guys here down at the bottom is, again, this whole idea that this process takes billions of years. We think Pangea has formed and broke up a number of different times. The problem with this is it's really difficult to prove this because as the continents move around, they're destroying crust. So, and again, that's the evidence that we're using to go back and take a look at what would happen on the Earth. Again, we don't have a time machine where we can go and take a look at those things. So what I provided to you guys is a series of notes. If you guys want to get a little more in-depth, these are a series of notes that I found online from the Tulane University Geology course. You can certainly go dig through that. And again, I've always told you guys, make sure you know where your sources are coming from. So these are the sites that I use to get some of the material for you guys to dig through today. So if you've got any questions or questions about the little quiz thing that I'll send out to you guys later on in the week, this would be a great series of sites to utilize along with these notes to help answer those questions. So this is the first. I'm going to try to do one or two of these videos a week, probably one while I take some time here. It's been a while since I've talked this much. But I want you guys to still get good quality science on the way to you guys, going to Terrebonne next year. So obviously stay safe, stay inside. Remember, make sure you're getting all your news source information from reputable sources like the CDC. You guys stay safe. I miss you guys. Hope you all are safe and enjoying your Easter break here. But after that, hopefully you guys, I'm definitely looking forward to talking some more about science, and I'll send you guys some next things. So the next thing that we're going to talk about, just kind of as a heads up, is going to be a series of information about volcanoes. So we're going to take a look at the different types of volcanoes we're going to have here. So stay tuned to the website, to my website. I'll try to post some information on that. The Google Classroom link, if you see someone or if you get an opportunity or you're texting one of your friends, send them the link to this. I still want to give you guys this opportunity to do those particular things. So from my house, if you heard anything in the background, that's my kids running around, my dog's running around. So from here, Mr. Willis, I hope you guys are being safe. Hope everything's going well for you, and keep reading about science. All right, guys, take care. Bye-bye.